and she'll talk on improved learning from Kolmogorov complexity.
All right. Hi, everybody. Yes, my name's Halley, if we haven't met, and I'm just going to be talking about this project that Valentine Cabinets and I have been working on recently. It's called Improved Learning from Time-Bounded Kolmogorov Complexity. Okay, so we've heard earlier in the program how there's this sort of interesting connection going on between pseudo-randomness and learning. So they seem to be somehow at odds with one another. There's like a sense in which one of them is only possible if the other is impossible. Okay, so I'm gonna illustrate that phenomenon with this very simple generator, which I'll call generator number 1. It's just like an M-wise direct product of this function f. So you can think of these xi's as strings of length n coming from some distribution, and f is just a boolean function applied to those strings. Okay, so it's pretty well known by this connection of Yao between distinguishability and predictability that this generator is not pseudo-random if and only if you can efficiently distinguish its outputs from the string with uniform distribution in the last m bits, if and only if you can predict the values of f of x given a prefix of the generator. So you can sort of predict it with probability a bit better than randomly guessing over that whatever distribution the xi's come from. Okay, so already in this statement of prediction, it kind of has like the flavor of learning, right? Because what's happening, we get some xi's along with the corresponding values of f on those xi's. So it's like some random examples of f. And then we're able to say something about an unseen value of f. So like we're sort of weakly learning f. I'll be a bit more precise about the kind of learning that I'm talking about. So this is Valiant's probably approximately correct learning. There's a learner and it's trying to learn some unknown target concept f, which is like a Boolean function. F belongs to a concept class C, which you could think of as like the set of functions computable by circuits of some polynomial size. And then what does the learner get? It gets some random samples x drawn according to the target distribution D, as well as the corresponding values of f on those inputs x. Okay, and then the goal is to produce with high probability a hypothesis H that approximates f well over the distribution D. There's a natural generalization of this model called Agnostic Pack learning. So we're still learning with respect to a fixed concept class, but now f might not belong to that class. So f can be arbitrary. It's probably too much to ask now that in polytime we could approximate some arbitrary f very well, but at least we could hope to do as well as the best concept that does belong to C. So trying to approximate f almost optimally with respect to C. And then there's also this relaxation of the model in which the learner is allowed to ask membership queries to the target function. So at any time in the learning process, it can come up with any string y that it likes and ask for the value of f on that input y. So there's this result of Carmesino, Impagliazzo cabinets, and Kolmogorov, which is kind of exploiting that antagonism between learning and pseudorandomness. Okay, so it says that if there's a natural proof of a circuit lower bound, like in the sense of Rasbarov and Rudich, then you can pack learn over that same circuit class, over the uniform distribution, and it'll require membership queries. Okay, so I'll just try to give like a little bit of intuition as to where the requirement of membership queries is coming from. Okay, so let's say we have a natural property. Let's try to use it to break this simple generator 1 that I started with, and we'll see what's going to happen. Okay, so we're learning over the uniform distribution. So we'll say that these xi's are uniformly random. Okay, and the goal would be to use a natural property to distinguish this from uniform. So we would want to show that the outputs of this generator would have smaller than trivial circuits if they're interpreted as a truth table. Okay, so yes, the xi's are uniformly random, so we probably can't hope to compress those very much. But we know F is computable by a small circuit, so intuitively you might think that using that fact you could compress this string. Say if you took M to be like sufficiently larger than the circuit size of F. Okay, but if you actually tried to construct a circuit doing that, you'd see that it doesn't really work, because this amount of randomness at the beginning is so long. Just the amount of like circuitry multiplexers you would need to take the appropriate xi and put it into the circuit computing F, it would overwhelm those M bits at the end that you had to work with. Okay, which is why the authors of CIKK had to resort to the slightly more complicated construction of Nissan and Vigderson. So yeah, I guess the most important thing here is that now the random seed Z is allowed to be much shorter than the stretch of the generator. And it's just kind of, the randomness is used very like economically, in that a small amount of randomness is kind of reused and reused to get different values of F. Okay, so you can kind of think of this as like a de-randomized version of the generator 1 that we started with. Or you could think of generator 1 as a really inefficient, design-free version of this generator. Okay, but the idea is that when interpreted as a truth table, outputs of this generator have smaller than trivial circuits. So we can break the generator, and then just by a hybrid argument, we can then predict the values of some unseen f of z sub i's given a prefix. Okay, and by the way, since z is uniformly distributed, those z sub restricted to f si's are just also uniformly distributed, which is what we want. Right, which brings me to what's with the membership queries. Well, once a learner fixes a choice of randomness, there are some very specific values of f that it would need to know based on that randomness in order to construct like that part of a hybrid. So it's not enough, as in the case of generator 1, to just have any random values of f. It has to be some very specific ones that depend on z. Okay.
In particular, it's no longer true that z restricted to si, what you want to predict, is independent of z restricted to s1. They share a few common bits in common, even if you fix all the others. You didn't know what those bits, what the common bits are. You want to know what.
Right. Yeah, thank you. So it's like, yeah, NW designs SI, right? Like they don't overlap too much, but they overlap a little
I'm
bit.
sorry, what are you proving now?
I'm just explaining why the CIKK paper needed to be able to ask membership.
But what is the result? That
That if natural properties exist, you can do pack learning, provided you have membership queries. Okay, so that's kind of high level, but that's the intuition. So some follow-up works have extended CIKK in different ways. So the same authors the next year show that you can also do agnostic pack learning if there's a kind of suitable generalization of natural properties. More recently, this paper from Benedict, Carmesino, Kolokolova, Ramya, and Sabin showed not only uniform distribution, but you can learn over an arbitrary, efficiently sampleable distribution. There is a caveat, which is that the learner needs to know the code of a sampler for that distribution. Okay, but I mean, in the case that D is just polytime sampleable, that's not too much of an imposition. It's just a constant number of bits.
How is the code used? How is the code of the sampler used?
I'm going to talk about that quite a bit later, so I'll answer that later. Yes, okay. So another way to think about natural properties, of course, is in terms of this minimum circuit size problem. So picking our definitions appropriately, the existence of natural properties is just equivalent to average case easiness of MCSP. So this is just a restatement of the CIKK result. It's the same thing. We've also heard a lot about these problems for time-bounded Kolmogorov complexity. So there's K superscript T, like K poly, and then there's Allender's K capital T. They're related to circuit size, right? Like K capital T, you can kind of think of it as a kind of a relaxation of circuit size, in that it does away with the requirement that a small description of a string be like interpreted as a Boolean circuit. So there's a little more flexibility intuitively. We've also heard that these problems are sometimes easier to work with, which is a little bit of foreshadowing for the next slide, which is that what we're able to prove if there's a K poly or K capital T like analog of a natural property, then you can do agnostic pack learning over any efficiently sampleable distribution, and you no longer need membership queries. So just learning from random examples. So I'll just be a bit more precise. It's average case easiness over the uniform distribution. That's just an analogy with what a natural property is. And then we're assuming like either a sort of one-sided or better yet, errorless definition of average case easiness. So we'd need that all yes instances of these problems are always going to be accepted, at least with high probability. As I said, the only access to the target function you get is through randomly drawn labeled examples. But there is a difference between the two cases in terms of the type of access you would get to the target distribution. So in the top case of K poly, all you need to know is an upper bound on the complexity of that distribution. So say if you knew those parameters T and A, then you could learn over any distribution that's sampleable in time A or T with A bits of advice. Okay, but in the bottom case of K capital T, it's the same situation I described before, where it's like a stronger form of access to the distribution. You need to know the code of a sampler. so sorry to do this to you. Just bear with me for a minute. I'll define K poly of X, denoted K superscript T. So you can think of it as what's the minimum length of a description that you could possibly send to some entity that can only run for T steps, such that it could recover the string X. There's also a probabilistic version of K-poly, where you'd think now of the sender and receiver as being in the presence of some shared randomness. And now the descriptions D are allowed to depend on that randomness. So what's the minimum length S, such that with high probability over randomness, there's some description of length S, which in the presence of the randomness yields the string X in time T. So it's like looking a bit like the definition of AM, in that like witnesses are allowed to depend on randomness. And then of course, this one's the most important complexity measure of the day because it's Allender's K capital T. So now we're asking about whether the string X is efficiently locally computable. So this decompressor on the left only needs one bit of X at a time. It's allowed to make random access queries to the description D. And now the amount of time T it takes is explicitly counted in the complexity of X. So now we'll talk a bit more about how our proofs work. So they're both working by these known reductions from pack learning to these problems that are called random right-hand side refutation. So there are a couple different versions of this, but this is kind of the simpler one from Vadan. So what is this problem? Well, we get some labeled examples, xi comma bi. So the xi's are strings from some distribution D, the bi's are bits, labeling the xi's. And then all a refuter has to do is distinguish between these two cases. So in the first case, the bi's are just independently uniformly random. And then in the other case, the bi's are consistent with some small circuit applied to the xi's.
Is P-samp now?
Yeah, it could be P-samp or P/polysam. Okay, so just some idea of how the reduction works. Why, if you can do this, can you do pack learning? Well, it's the same reason that you can do some learning if you break that first generator that I was talking about, right? So I think it's kind of clear that if you can solve this problem, you can break that generator. It's just kind of a rewriting of the same thing, distinguishing whether the labels are random or the outputs of a small circuit. If you can do that, then you can at least weakly learn that function F over the distribution D. And if you want to boost it and get like a stronger learner that knows F a lot better, then okay, you can do boosting and the distribution will change a bit, but if you can refute over all of P-samp, then you can also agnostically learn over all of P-samp. But it's like distribution independent in that sense. Okay, and then there's this other version that was given independently by Kothari and Livni. And it's been called correlative random right-hand side refutation. So it's just kind of a version of the problem that turns out to be equivalent to agnostic pack learning. So everything's the same here, except in the soundness case. Now the BIs aren't exactly the values of F on the xi's, but they are correlated with those values.
here, are we still assuming like all the xi's are independent and the labels are independent? Or could like they just adversarial pick which CIs are going to equal the label?
It's everything's independent. Okay, and then yeah, also kind of by a hybrid argument, you can show that if you can do this refutation problem, then you can agnostically pack learn F. And the nice thing about the agnostic setting is that there's a distribution specific boosting. So if we can refute over this one distribution, we can strongly agnostically pack learn over the same distribution. Now I'm going to claim that with these tools in hand, under our assumptions, it's already easy to learn over the uniform distribution. Okay, so for example, let's assume that Allender's KT is easy on average and see what happens. Okay, so now the xi's are independently uniformly random, so are the bi's. So if we concatenate them all into one big long string, call it x comma b, well, we know that with very high probability over uniformly random strings that those strings will have almost maximum KT complexity. So on the random side, the whole string is uniformly random, probably will have KT complexity about its length. And now I want to show that in the correlative case, there's some KT compression going on. Okay, so the xi's are still uniformly random, no hope of compressing those, but once we have the xi's, we can kind of show that it'll be easier to compute the b's. So what do? We'll give ourselves enough bits to write down all of x, and we give ourselves enough bits to write down the size of a circuit that computes f. And that's a step in the right direction, right? Because if we want some bi, we could just look up the corresponding xi, run it through the circuit for f, and then we have the value of f on x sub I. Okay, but that's not quite enough, of course, because the bi's aren't always correct with respect to f. So that's where this term comes in, which is kind of encoding the indices I where the bi's are incorrect. I won't go into too much detail, but it turns out to be a little bit KT compressible. You can choose M to be a large enough polynomial in N, so that like M for sure outweighs the size of the circuit for F, and you get the desired gap in KT between the two cases, which your heuristic for KT can identify and output random or correlative. Right. Yeah.
So, why is it order m to the 3/4? Oh, okay. So the m that you picked is exactly the same as the advantage in the correlation, or it's related to that advantage?
Yeah, it's
Yeah,
related.
otherwise you don't get compression.
Right. So that's why I was wondering why it wasn't like m. Right. Set. So you have to like pick the m to be about that, the first poly in negative n to the 4th power or something.
Oh yeah, that's right. That's right.
Okay.
Yeah. Okay, so let's see what goes wrong if we try to apply the same argument to learn over other distributions. Okay, there are a couple problems. And one is that we've only assumed we have a heuristic that works over the uniform distribution. And that's fine in the correlative case because of the nice one-sided error property we've assumed. But in the random case, now the xi's aren't uniformly random, and we have no reason to believe our heuristic's going to work very well. Okay, and then the other issue is that with the xi's being sampled according to D, there's no reason to think that their KT complexity is likely to be large anymore. So we'll have to think of some way to get around that. Which is where this paper from Shuichi Hirahara and Mikito Nanoshima comes in. So it's kind of providing a framework to get around those obstacles that I mentioned. They're working under the assumption of distributional NP being an average P, and then they're able to get the same kind of conclusion that we get in the case of our K-poly result. So that like cuts our work out for us, right? We want to try to apply their framework under this weaker starting assumption. Okay, so I'll just say a little bit about that framework. This is kind of the first ingredient of it. So under that assumption, this average case easiness assumption, you can prove a worst case approximation algorithm for K-poly. So for any string X, you can efficiently compute a value S that is like some sort of estimate of K-poly of X. Okay, and then the second ingredient is a weak symmetry of information theorem for K-poly. So it's worst case with respect to the string X, but for any string X with high probability over a uniformly random Y, K-poly of X and Y together will be roughly at least K-poly of X plus the length of Y. So the second ingredient, I'll just apply it immediately to this refutation problem. So it just tells us right away in the random case that K-poly of X and B together is going to be roughly at least K-poly of X plus the length of B. Okay, and I'll just move some of these terms over a bit, and this shows how we would use the first ingredient, which is the approximation algorithm for K-poly. So we would estimate the values of K-poly of X, K-poly of X and B together, subtract them, compare them with a threshold, and output an answer. Okay, but if you're paying close attention, you might see that there's some sort of issue in that the K-poly of X term has different time bounds on the two sides. And that's necessary given the weak symmetry of information and the argument that we used in the correlative case. So how do we get around this? Well, the authors give what I think is a really elegant and powerful way around this. So it says that, well, under the average case easiness assumption, for any efficiently samplable distribution D, for sufficiently large time-bound T, so like a big enough polynomial in N, say, and for X sampled according to D, the expected difference between K-poly of X and time unbounded K of X is not going to be too large. So it'll just be some error that depends like on the complexity of the distribution. It's not too much for us because we can choose a number of samples M that like far outweighs this. But yeah, the upshot is that with high probability, we don't have to care too much about the differences between KPT of X and KT over 2 of X because there's just this nice sort of smoothing out effect in the expectation. Both are going to be close enough to just K of X.
So this is not just assuming that K of X is easy on average, but all system T is easy on average. So this is where you have to improve something. Okay.
So now I'll just say a little bit about kind of how we step from an average case assumption to like a worst case conclusion. So we want to show that some strings y have k-poly compression via this sort of generator reconstruction. This is what Shuichi was talking about earlier, this direct product generator. But we want to use the reconstruction property of this generator to show that k-poly of y is compressible. Okay, so we take a string y and we encode it in this generator, and we set things up in a way that we know there's a distinguisher between that generator and the uniform distribution. And then the nice thing about the generator, of course, is its reconstruction property. So it can give us back the string y that we started with, although it's randomized. But that's okay if distributional NP is an average P, because by Berman, Fortno, and Pavan, we have de-randomization. So we can de-randomize this reconstruction procedure. The randomness R becomes fixed, and then the required advice string for Y, which depended on R, also becomes fixed. So we have that there are some short advice string alpha that can compute Y in polynomial time. Okay, but of course this doesn't work anymore. Under our weaker assumption, we don't have de-randomization. The randomness R is kind of long. Alpha depends on the randomness, so it certainly doesn't seem like there's any k-poly compression happening for Y. But it turns out what we do get is probabilistic k-poly compression. So the definition of pk poly fits the situation perfectly. And that's not actually an accident, but we have that with high probability over randomness R, there's some short description, namely alpha of Y and R, that can compute Y in polytime in the presence of R. Okay, so this is what we have to work with right now. Let's try to just plug it into the framework of Hirahara and Nanashima and see what comes out. Okay, so we still get a worst case algorithm that does something, but okay, now for any string X, we can get a value S that's kind of sandwiched in between like pk poly of X and k poly of X. So a priori, this doesn't look like it would be very helpful because in general, pk poly and k poly can be as far apart as you'd like. There's nothing tying them together. Okay, so how do we get around this? Well, the idea would be to use something like this slide I showed earlier, which says that in the expectation, kt of X will be roughly k of X. One thing we know about pkt is that it's always smaller than kt and it's always larger than time unbounded k. So if we had a statement like this, it would immediately give us that we don't need to worry too much about these differences between kt and pkt because with high probability they'll be close enough. With high probability that approximation algorithm will be good enough for our purposes. Okay, but of course, we can't show this exactly without the assumption with all of NP. But it turns out that we can show something that looks a bit similar. Okay, and I won't go into the exact reason of why we can't show this. It has to do with a source coding theorem for k-poly that you can prove under this assumption. Okay, but without that, we can show that this holds. So it's exactly the same, except now it requires this presence of this uniformly random string R. Okay, but the expected difference over X sampled from D and uniformly random R of that difference between K poly of X and R, K of X and R is not going to be too big. Okay, so yeah, what do we do with this?
And that previous one, I guess, doesn't this make any assumption?
Totally unconditional.
But can I think of it as like, it's like a conditional expectation over this randomness of the gap between the. Could you please repeat the question? Is it like a conditional expectation of the gap between these measures for the shared randomness? That's fine. We'll take it on.
Yeah, great. I mean, it's not conditional. This is the expectation over random R. But yeah, what we do with the randomness, we just incorporate it into the refuter algorithm itself. So the refuter is allowed to be a randomized entity. It has plenty of uniform randomness at its disposal, so it can just sample an R and then use that worst case approximation algorithm to estimate K poly of X and R, or K poly of X, B and R. And it turns out that the gap between the two sides is still intact after the modification there. Okay, yeah, so there's this one other issue I haven't addressed yet, which is the weak symmetry of information theorem. Admittedly, there might be different ways around this. So you can maybe imagine a solution like the one I explained before. You could have PK poly on one side, K poly on the other side, or something like that. But I think a nicer way around it is just to observe that you don't need this kind of statement at all. And it's just for the same reason I've been citing, the expected closeness of time-bounded and time-unbounded K complexity. You can just apply the, fact of symmetry of information for time-unbounded Kolmogorov complexity. Okay, so that's all I have to say about the K poly result. So now I'll switch gears to the second one for Allender's KT. Just to review the situation, we don't have a lot of those tools that we had in the case of K poly, like a worst average reduction or KT compression via generator reconstruction. Okay, so all we really have to work with now is the assumed heuristic for MKTP, and it only works over the uniform distribution. Okay, but at least we know that we can learn over the uniform distribution from this assumption. So our goal now becomes to reduce the task of learning over an arbitrary distribution to that of learning over the uniform distribution. To do that, we use distributional inversion of Impagliazzo and Luby. This was used in a similar way in that paper of Benedict et al. That I mentioned earlier. So it's kind of inspired by that. Okay, but what's a distributional inverter? Well, what's a standard inverter for a purported one-way function? Given some output y of that function, it's supposed to produce a preimage of y. Seems a little bit harder for a distributional inverter in that it has to produce a nearly uniformly random preimage of y. So any arbitrary preimage wouldn't be good enough. This paper shows that the two notions are actually essentially equivalent. And luckily for us, under our assumption, we have distributional inverters for all polytime computable functions. That's shown in a work of Allender et al. Okay, so back to this problem of random right-hand side refutation. We're trying to learn over a distribution D, which is samplable by a poly-size circuit C. what does that mean? It means the distribution D is identical to the distribution of C applied to the uniform distribution, which is the definition of a sampler. And we're given some samples xi with labels bi. What do? Well, we take a distributional inverter for that circuit C that samples D, and we apply it to the first X part of each one of our samples. And then just from the definitions of D and C, and by the property of distributional inversion, we get like some simulated samples, Ri comma Bi, where the Ris are now nearly uniformly random. And yeah, we just keep the same Bis with the corresponding Ris. Okay, so just reviewing the problem we want to solve, this top one. In the correlative case, we know that the Bis are correlated with the outputs of F over the distribution D. Down below here, I'm not doing anything. I'm just restating this. So this statement is exactly equivalent to this statement. This distribution D is just the distribution of C applied to the uniform distribution. Okay, so that's just a rewriting. We apply the transformation to the samples that I mentioned earlier, and you can see how this kind of sets up a new problem of refutation, which is happening over the uniform distribution. And we know we have an algorithm solving the bottom problem. Now, I'm just going to claim that the answers to the bottom problem are still correct with respect to the top problem. Now, in the random case, it's easy to see that in the random case, we'll still be random at the bottom. In the correlative case, okay, so they're correlated with a small circuit F. Down in this case, the outputs are still correlated with another small circuit, namely F composed with C. Okay, so we'll output correlative, and it's the right answer. That's it. So that's how the proof goes for K capital T. Just a couple open problems, which I think are very obviously unresolved by this work. One would be to try to do away with that kind of strong access to the distribution that we require in the case of Allender's KT. I don't know of any reason why we shouldn't be able to do that other than just not knowing how. And then the bottom one is probably like a bigger problem, but it would be great to get from natural properties to learning just from random examples. I'm like vaguely aware that there would be some implications in cryptography to do with construction of weak PRFs in certain circuit classes.
Are there any questions? I have a question. So like in CIKK, we showed like versions of like MCSP for different natural properties for weaker circuit classes. Would it make sense to look at KT for weaker kinds of algorithms and see whether it actually is plausible to come up with, can we come up with a weak enough type of algorithm that we could actually come up with a heuristic for KT?
Yeah, I think it's a good question. I mean, it's kind of one like obvious disadvantage of going to KT rather than circuit size is that it doesn't really fit into like known proofs of circuit lower bounds or anything like that, but I think it'd be a good direction to explore.
Yeah. We'll have a short coffee break and then we'll resume at 3:25.